Hello again, grade 7s. In today's lesson, we are going to wrap up the patterns and expressions unit of study, and we're going to do that by looking specifically at linear relations, which is something we've already been doing throughout the unit. We just haven't properly defined what a linear relation is yet. The learning outcome is to create a table of values from a linear relation, graph the table of values, and analyze the graph to draw conclusions and solve problems. Okay, so let's start off by defining what a linear relation is. A linear relation is a pattern made by two sets of numbers that result in points along a straight line on a Cartesian plane. Okay, so what this basically means is if you look at a pattern and if you can actually plot the data on a Cartesian plane, the data, you should be able to put a straight line through it. Okay, so here's an example of one. I don't really understand the context of this graph. It says number of pups and number of fish. Okay, but nonetheless, the data has been plotted, and you should be able to take a ruler and you should be able to put a straight line through this data. I mean, not that I'm going to be able to do this with the drawing tablet, but if you had a ruler, you could make a nice straight line that goes through the data. Okay, so if your pattern made by two sets of numbers can form a straight line on a Cartesian plane, we call it a linear relation. And again, whenever you see that word linear, just look at the first four letters of the word. Okay, the first four letters of the word is line. So linear relation is all about being able to put a straight line through the data. Here's another one, an absolutely horrible resolution. This one, again, if you plot the data based on a pattern formed from the two sets of numbers, if you can put a straight line through the data, then it is a linear relation. So let's see how well I can do this. I guess that's acceptable. Okay, just a quick review, since we're going to have to actually plot points on a Cartesian plane. When we plot points on a Cartesian plane, we need our points to be presented in a format that's referred to as an ordered pair. So an ordered pair is in the format bracket x comma y close bracket. X represents the horizontal coordinate, so that tells you, starting from the origin, where should you go, left or right. And again, you go to the right if the x coordinate is positive, and you go to the left if it's negative. And the y coordinate is going to be the vertical coordinate, which means after you've moved whatever distance horizontally, then you would go up if the y coordinate's positive and down if the y coordinate is negative. Okay, so let's do a couple of examples. So it says example 1, there are 20 bananas in a fruit bowl. Raul takes 2 bananas each time he enters the kitchen. A, write an expression relating the trip number into the kitchen and the number of bananas remaining in the bowl. Okay, this is hard. Okay, so what it's asking us to do is it wants us to build an equation that we can use to calculate how many bananas are left in the kitchen based on how many trips are made into the kitchen. So to make an equation, we have to pick some variables and define them. So I'm going to say let t equal the trip number. And then I'm going to let b equal number of bananas remaining, or number of remaining bananas. Okay, so I need to build an equation that's going to allow me to calculate b if I know what the trip number is. Okay, what I'm going to do is I'm going to just write down a phrase that describes the pattern here, and we'll see if we can take that phrase and turn it into a mathematical equation. Okay, so usually when we describe a pattern, we go in the format starting with this, do this to get to the next term. So what are we starting with here? Well, we're starting with 20 bananas in a fruit bowl. So I'd say starting with 20 bananas. Okay, so starting with 20 bananas, what are we doing? We're removing, so we're taking away, so we're subtracting for removing them. Subtract 2 bananas for every trip into the kitchen. All right, so let's see if we can take that statement and if we can write down an equation. So the equation I want an equation that's going to allow me to calculate the number of bananas that are remaining. So that's B. Okay, so what does it say? Starting with 20 bananas, we'll say B is equal to, okay, starting with 20 bananas would be 20. We're going to remove or subtract 2 bananas. So it's going to be subtract 2 bananas. So starting at 20, remove 2 bananas for each trip into the kitchen. Now, the trip number into the kitchen is a variable, so we're going to represent that with a t. So we'll say B is equal to 20 minus 2 times t. Okay, so let's double check this again. So how many bananas are left? Starting with 20, remove 2 bananas for each trip into the kitchen. Okay, this is hands down the most difficult part of this problem, is to come up with the actual mathematical equation to do this. Okay, so that'd be 20 minus, we don't need to show the multiplication operator, it's just implied, 20 minus 2 times t. Okay, B, it says create a table of values showing the number of bananas remaining after each of the first 6 trips into the kitchen. Okay, so we'll do 2 columns. So we'll do trip number. And then we'll do number of bananas left. Okay, let's put a horizontal line across here, and then we'll do a vertical one to separate the column. Okay, so it says due for the first 6 trips into the kitchen. So trip 1, trip 2, trip 3, trip 4, trip 5, trip 6. Now, to calculate the number of bananas remaining, we could use the linear relation equation I have here, but we can actually just identify this like by just thinking of what's happening. Okay, so after you make the first trip into the kitchen, actually I'm going to start over again here. Just I want to include trip 0, so which means that we haven't made a trip into the kitchen yet. Okay, so let's do 0, 1, 2, 3, 4, 5, and 6. Okay, if we've made no trips into the kitchen, then you just have the starting amount of bananas. That would be 20. Now, every time I make a trip into the kitchen, he takes 2 of them away. So after trip number 1, there'd be 18 left. After trip number 2, there would be 16 left. After trip 3, take away another 2, 14. After trip 4, there would be 12. After trip 5, there would be 10. And after trip 6, there would be 8. And again, if I want to, I could use the linear relation and use a substitution method to confirm those are correct, but there's no need to do that because we can see the pattern pretty clearly from the table of values. Okay, so that's B. Now C says, what I want to do is I want to plot the data from the table on a Cartesian plane. Okay, so to do this, we need to form ordered pairs. So to form an ordered pair, I'm going to treat the trip number as my x coordinate. So let's say the trip number is my x coordinate, and the number of bananas is going to be your y coordinate. Therefore, your first ordered pair would be 0, 20. The second one would be 1, 18. The third one would be 2, 16. Third ordered pair would be 3, 14. And then 4, 12. And then 5, 10. And then 6, 8. Okay, so now let's go to the graph. Okay, first things first, label the graph. So on the x-axis, we're going to make that the trip number. So let's write down a title here for trip number. Trip number, which we use the variable t to represent. And then on the vertical axis, we are going to identify the number of bananas. Okay, so this is going to be a little tricky for me to write down here. Okay, let's see how well I can do this. Okay, so we'll do number of bananas. This is really, really hard to write it like vertically on a drawing tablet. Okay, we should put a title above the graph as well. And I don't know what we should write here. Let's call it Banana Thief or something like that. Although he's not really a thief because presumably he's allowed to eat those bananas, but so I'll say Banana Thief or something. I can't think of anything else more creative. Okay, so now let's plot the points on the graph. So the first point is 0, 20, which means starting at the origin, don't go anywhere left or right, and just go all the way up to 20. So my first point is going to be located all the way up here. Second coordinate is 1, 18. So that means go 1 to the right and then go 18 up. So 1 across, go 18 up to the top here. So 18 would be halfway in between 20 and 16. Then we have 2, 16, which means starting from the origin, go 2 to the right and then go 16 up. So that would be located here. And then starting at the origin, so 3, 14, so we go 3 to the right and then 14 up. So this would be located at this position. And then 4, 12, so we go 1, 2, 3, 4 to the right, and then we go 12 up. And then back here, 5, 10, which means starting at the origin, go 5 to the right and then 10 up. So that would be located at this position. And then we have 6, 8, which means starting at the origin, go 6 to the right and then go 8 up. Okay, so this clearly is a linear relation because you could take a ruler and you could make a straight line go through the data points. Okay, so that's my graph. Now, part D says how many bananas are remaining after 8 trips. Well, there's actually 3 ways you could do this. You could just extend the table of values down to trip number 8, and in which case I think after trip 7 you'd have 6 left, and after trip 8 you would have 4 left. The other way is we may as well use our expression because we haven't done anything with it so far. So let's use a substitution method and see what we can get here. So 3-step procedure would tell me, first step, write the equation down. B is equal to 20 minus 2 times t. And we're going to do a substitution. We're going to plug in for the value of t. So it says after 8 trips. So we're just going to plug in t is equal to 8. So do a substitution. Okay, so let's plug this in. And then this would be b would be equal to 20 minus 2 times 8. Okay, careful with the order of operations. We don't want to do the subtraction first. We want to do the multiplication. So we're going to do 2 times 8 first. So this would be 20. Minus 2 times 8 is 16. And then 20 minus 16 would just be equal to 4. So that means after 8 trips, you would have 4 bananas that are left over. Now, there is another way you could do it as well. So I mentioned you could extend the table of values. You could also just use the equation to calculate the number of bananas. You could also use the graph. Okay, so part of the reason that we want to plot linear relationships is that we can extrapolate the data. So extrapolate the data means we can use it to make future predictions. So here's how I would do it. Okay, what best models the graph here? A line of best fit. So the line of best fit would just go just keep going down. Okay, straight down like this. Okay, so what it wants us to do is we can use the line of best fit now to figure out how many bananas are remaining after 8 trips. Okay, so the x-axis is the trip number. So what I could do is I could just go up to the line of best fit. So here would be the point. And then just go horizontally across to read where it hits the y-axis. And again, this should hit it because we already calculated this at 4. Okay, so that does make sense. Although, quite frankly, what doesn't really make any sense though is like you like putting a solid line through here doesn't make a whole lot of sense, because that implies that, like, for example, you could have a point right here, but you can't. Okay, you can't have a point right here because what trip number would that be? So that'd be trip number 0.5. You can't make half of a trip. You either do the trip or you don't. There's no in between there. So maybe instead of doing a solid line like what I did here, the better thing to maybe have done would have been to do a dashed line, just to indicate that the line itself is not really continuous, but we can still use the line to make an extrapolation. Not a huge deal. I mean, if you did this solid line, I don't think I'd be upset about it at the grade 7 level, but as we start to make more sense of like what our data represents, I think a dashed line would be more appropriate here. All right, I have a second example. I did not include this in the notes booklet, so if you'd like, you can just write it down on a separate piece of paper. Okay, so it says the relationship n and then 3n plus 1 can be written as the linear function f equals 3n plus 1. And it wants me to make a table of values for n equals 0 through 6. Okay, so this is, we kind of did this in the last lesson, part A anyways. Part B is going to be a little bit different. Okay, so let's make a table of values. And we'll do 2 parts of the table. So one part of the table of values is going to have my values of n, and the other part of the table of values is going to have the value of f, which we can calculate by going 3n plus 1. Okay, so that's going to be my table of values. Okay, so we want to do n is 0 through 6. We have 0, 1, 2, 3, 4, 5, and then 6. Now, we have no pattern to look at here, or no description of the pattern. So what we have to do this time around is we must use this equation to actually calculate what the f value is going to be. Okay, so in the equation, let's start off by doing a substitution when n equals 0, and we're going to plug it into the equation f is equal to, and again, if you have 3n, multiplication is the implied operation, so you have 3 times n plus 1. Okay, let's do a substitution now. We're going to plug in n equals 0, so that would be 3 times 0 plus 1. 3 times 0 is 0, and then plus 1 would give me f is equal to 1 when n equals 0. That's the first part. Okay, let's do n equals 1 and plug it into the same equation. So we're going to plug it into the equation. F is equal to 3 times n plus 1. So when I sub that in there, that'd be f is equal to 3 times, this time around we're going to plug in n equals 1 for n. 3 times 1 plus 1. 3 times 1 is 3, plus 1 is going to be equal to 4. So let's put that in the table of values here. And then we'll do one more, and then we'll be able to figure out what the pattern is. So then we have n equals 2, and then you have f would be equal to 3 times n plus 1. So this would be f is equal to 3 times 2 plus 1. 3 times 2 is 6, plus 1 would be equal to 7. Okay, so what's going on in the pattern here? Well, for the f values, I'm starting with 1, and to get to the next term for f, I'm just adding 3 every time. So then 7 plus 3 would be 10, 10 plus 3 would be 13, 13 plus 3 would be 16, and finally 16 plus 3 would be 19. Okay, so usually you need about 3 calculations to figure out what the pattern actually is. Okay, B says draw a graph using the ordered pairs from your table. Okay, so I'm not going to write the ordered pairs out, but the way we're going to do this is going to be your x coordinate, and this is going to be your y coordinate. So we're going to first of all plot 0, 1. Okay, so 0, 1 would be starting at the origin. Don't go anywhere left or right and just go up to 1. Well, this would be 2. So therefore, 1 is going to be located here. We should label this, by the way. We'll say that this is n. And then this here is going to be, again, let's try to write this vertically, which is like borderline impossible. F is equal to 3n plus 1. Okay, I was a little bit better this time. And maybe just the title of the graph. We don't know what f and n represents. Let's call it a linear relation. Okay, so let's go back here. Your second coordinate would be 1, 4. So that would mean starting from the origin, go 1 to the right, and then go 4 up. So then we're going to be located right here. Next point would be 2, 7, which means starting at the origin, go 2 to the right, and then go 7 up. So this would be 6. So 7 is going to be located right here. Okay, and then we have 3, 10, which means starting at the origin, go 3 to the right, and then go 10 up. And then we have 4, 13. So starting at the origin, go 4 to the right, and then go 13 up. So that's going to be located right here. And then 5, 16, which means starting at the origin, go 5 to the right, and then go 16 up. And then the final one, 6, 19. So starting at the origin, go 6 to the right. So go over to 6, and then go 19 up. 19 would be halfway between 18 and 20. So we've got it right here. And this indeed is a linear relation because you could take a ruler and you could make a straight line go through it. Okay, one more. So it says, what is the value of f if n is equal to 50? Now, I intentionally chose a large value because there's really only one method you can use to calculate it here. That's practical. I mean, you could take the table of values and extend it down to an n value of 50, but that would just be insane. Okay, like you use almost an entire piece of paper just to do that. The graph you could also do, but you'd have to extend the range of the y and the x-axis to like x is 50. Like the graph would be enormous. Again, not practical. What is practical is using the equation f equals 3n plus 1. So all we need to do here is when n equals 50, we're just going to do a substitution. So these are three-step procedures. So we'd have f would be equal to 3 times n plus 1. We're going to replace n with 50. So we'd have f is equal to 3 times 50 plus 1. Order of operations, 3 times 50 would be 3 groups of 50 is 150. And then we're just going to add 1 at the end. Therefore, f would be equal to 151. Okay. All right, so in the MathLink 7 textbook, you can complete the assignment on pages 378, 381. Just do 5 questions. Do 3, 4, 5, 6, and 10. Now, you're going to have to plot a graph for some of these questions. And if you don't want to make the grid by yourself, what I'll do is in the content section on D2L, under the lesson on linear relations, I'll put in a Word document that has graphs that you can use to plot the data for the questions where you actually need to do it. So you can print that off if you want to save yourself a little bit of work. And that's it for this unit. And then I'll talk to you in the final unit of study for Math 7 dealing with some basic algebra. Well, we've actually been getting into some basic algebra already, but we're going to start to worry about solving equations.